Hey folks, welcome to another online lesson, and today we're now going to move on to look at latent heat, and we're going to use the term phase change correctly, define and use latent heat, and in the second part of the lesson look at how to use latent heat and specific heat capacity in calculations. So first of all, when we look at a kettle when it's boiling, what's happening? Okay, so pause the video and have a wee think. Hopefully you can tell me that the water in the kettle is boiling. Now the thing I want you to make a note of is that steam, most people would say would be this stuff here. Now this is actually not steam because the water has already turned back into a liquid. The steam part of evaporated water is actually this bit here, the invisible bit. And this is the bit that is actually steam because you can't really see it. Now, when a phase change happens, this is when a substance changes from one state to another. And you may remember from first, second year science that a solid will melt into a liquid evaporates into a gas, and then a gas condenses into a liquid, and a liquid freezes into a solid. And those are the kind of phase changes that happened. And we're using water because water is one that can actually happen at room temperature. It can be an ice at 0 degrees Celsius. It can be a liquid between 0 to 100 degrees Celsius. And at 100 degrees Celsius, it boils into a gas. Now, if we were in class, I would show you this cooling curve experiment. And the idea of this is to cool a liquid down to a solid. So the setup for this experiment is that you have a beaker with cold water here to speed up the cooling process. You then have a test tube with this chemical called cetyl alcohol or stearic acid. And we use this because when it's a liquid, it's clear like water. But when it's a solid, it becomes like a wax or like candle wax. And what we do is we have a temperature probe, and this measures the temperature as the cetyl alcohol cools from a liquid into a solid. So we're measuring the temperature as it cools down, and also, more importantly, when there is a phase change from a liquid to a solid. Now, if you want to see this experiment for real, then try this link here. I will include it so you can click on it later on. And that shows you the experiment at work. Now, let's look at a graph of those results, assuming those results were absolutely perfect. So we have a graph here where there's temperature on the y-axis in degrees Celsius, the time which is in seconds. So as the time increases, you can imagine the liquid is cooling down, so it's getting colder. It then undergoes a phase change, i.e. from a liquid into a solid, so it freezes from a liquid to a solid, and then the solid will continue to cool down, so it gets cooler. And the key thing I want you to take away from this graph is that when a liquid freezes into a solid, its temperature stays the same. So there's no temperature change. And we'll look at that later on to see why that is. Now, let's look at the situation where the substance is being heated up. So again, we have temperature on the y-axis and we have time on the x-axis. So as you'd imagine, you're heating up a solid, it gets hotter. It then undergoes a phase change, i.e. it melts from a solid to a liquid, and then the liquid will start to get hotter. And so the key thing here is that, again, when there's a phase change, i.e. when the solid melts into a liquid, the temperature stays the same. The other thing as well is notice this shape of this graph is exactly the same as the other one, it's just we're kind of going in the opposite direction. Now, to pull this all together, because we know we have three states of matter, a gas, liquid, and a solid. So when it's a gas changing to a liquid, because it's cooling down, it condenses, and again, the temperature stays the same. And similarly, when a liquid freezes into a solid, the temperature stays the same. So these phase changes, the key thing is there is no temperature change. Similarly, if we're heating up a substance, then a solid will melt into liquid where the temperature stays the same. And then finally, the liquid will evaporate into gas and the temperature stays the same. So again, notice that the shape of these graphs are very similar. It's just they're kind of reversed or flipped over because we're going from one to the other. So a question you might be asking is, why does the temperature stay the same when a substance is changing state? Well, to kind of give you a wee clue about this, let's think about what we know so far. So some useful prior knowledge is number one, is that heat is a type of energy measured in joules, because remember, we're giving the substance heat energy. And generally, if you heat something up, you increase its temperature. But remember, temperature is a measure of the average kinetic energy of the particles that make up that substance. So two questions to kind of get you thinking about this. Number one, why does adding more heat energy not increase the temperature? Which might lead you to ask the next question, what could the heat energy be used for instead? Because it can't disappear, remember that's conservation of energy, so what is the heat energy being used for? And the answer is on the next slide. So first of all, if you imagine our liquid going into a gas, well remember for our liquid, some of the atoms are still held together in bonds, but they are free enough to move. Whereas in a gas, the atoms don't have very many bonds and they're moving around very quickly. So in order to go from one to the other, you must use energy to break those bonds. And it's because that energy is used to break the bonds, there's no energy left, if you like, to make the atoms go faster. So you can now see why we really have to have a very specific definition for heat energy and temperature. So in summary, the energy needed to change the state of the substance is called the latent heat. And latent, because latent means it's kind of hidden. Because if you think about it, that heat energy is hidden in the substance because it's used to break the bonds. It doesn't change its temperature. Now, just to summarize, just to show this in a slightly different form, we've got a second graph where we've got temperature on the y-axis, and notice we now have heat energy. So as heat energy increases, the solid will go into a liquid, and the liquid will go into a gas. As heat energy decreases, a gas will go into a liquid, and a liquid will go into a solid. And the two key phase changes are when a liquid is going into a solid, or a solid is going to liquid. And this one we call the latent heat of fusion. The second one is between the liquid and a gas, and that one we call the latent heat of vaporization. And these are the two latent heats that you must be able to know and also be able to use. Now, to give you a proper definition or explanation, latent heat of fusion is the energy needed for a substance to change from a solid to a liquid or a liquid to a solid. It goes both ways. So it doesn't matter if you're going from a solid to a liquid or a liquid to a solid, you use the latent heat of fusion. Similarly, the latent heat of vaporization, that's the energy needed for a substance to change from a liquid into a gas or a gas into a liquid. So a final question here is, which latent heat do you think will be bigger? The latent heat of fusion, going from a solid to a liquid, or the latent heat of vaporization, going from a liquid to a gas? Now I'll give you a clue. Look at the diagram and think about which one would take more energy to go from a solid to a liquid or a liquid into a gas. Okay, hopefully you got the answer is that the latent heat of vaporization is generally bigger. Can you think of why? Well, the answer is, if you look at the diagram, here you're not breaking as many bonds as if you were going from a liquid into gas. Because remember, in a gas, there's very few bonds to hold the particles together, so that means you need more energy to make them into separate kind of particles. Whereas going from a solid to liquid, you've still got some bonds left, so you don't have to use all that energy to break the bonds apart. So to summarize, in general, vaporization is bigger because more bonds need to be broken into to make a liquid into a gas. And if you follow through to the next lesson, we'll look at some calculations and how we use these latent heats.